Hello and welcome to review for Unit 3 of Intro to Logic. Today we're doing translations review. Let's go back to the very basics of the language we're talking about. So in predicate logic, we use lowercase letters A, B, C, up through W as names of specific individual persons, places, or things. We don't use them for plural or count noun phrases. They have to be a name of a specific person or a specific place or a specific planet. Things like Kevin, France, Neptune. We don't use letters X, Y, and Z for names. We use those as variables, which we'll get to in a bit. But it's very easy once you've gotten used to using variables for a lot of things to forget that we use letters at the beginning of the alphabet for specific individual persons, places, and things. So don't forget that. We use uppercase letters for things we say about the subjects, things we say about the things the lowercase letters stand for. So properties, traits, characteristics, or relationships between things. We write those first and followed by the lowercase letters to make whole statements. So we use monadic predicates as the predicates that apply to one thing when it's a property a thing has on its own. We use polyadic predicates, that is, predicates that stand for relationships between multiple things when we're talking about a relationship between multiple things. So TK would mean Kevin is tall, or might mean Kevin is tall. T for being tall, lowercase k for Kevin. We put the predicate first. Lowercase l, FA might stand for France is larger than Amherst. That's a relationship between two things. So after the uppercase L, we write two lowercase letters, one for France, one for Amherst. Neptune is a planet, P for being a planet, lowercase n for Neptune. Neptune is larger than France. Again, we have the same relationship we had in the earlier example, but now the two things are Neptune and France. Make sure you pay attention to the order. The order matters with polyadic predicates. So uppercase L for being larger than, lowercase n for Neptune, lowercase f for France. DF might mean France is democratic. Now, since we don't use X, Y, and Z as names, if you have a name that starts with an X in English, like Zena, you'll want to use the next letter after the X, like an E for Zena. So AGE might mean Gabrielle admires Zena. A for admiration, lowercase g for Gabrielle, lowercase e now for Zena. We won't use lowercase x. We're going to leave x as a variable. So we can have more complicated statements. You can have and between names or between names. You can have and between adjectives or predicates. And sometimes we translate those with the ampersand sign or the wedge sign. And sometimes we use a polyadic predicate instead. Now, it depends upon whether the statement can be broken up into two separate thoughts. So when it can be broken up into two separate thoughts, we reword the entire statement so we have and between two entire statements. So France and Britain are democratic, we write DF and DB because we break that into two thoughts. One, France is democratic and Britain is democratic. Either Orion or Callisto is a constellation, we can break that into two separate thoughts. Either Orion is a constellation, CO, or Callisto is a constellation, CC. Sanjukta is intelligent and talented. Here we've got the and between two adjectives. We can break this into two separate thoughts again, though. IS means Sanjukta is intelligent, and TS, Sanjukta is talented. Here we repeat the name rather than repeating the predicate. We've got two different predicates, but they're applied to the same individual. But number 4, Mercury and Pluto are similar. Here, this is a relationship between Mercury and Pluto. It doesn't mean Mercury is similar and Pluto is similar. It means Mercury and Pluto are similar to each other, or just Mercury is similar to Pluto. When you have something like this, when you can't break it into two separate thoughts, you want to use a polyadic predicate. Uppercase S for being similar, lowercase m for Mercury, lowercase p for Pluto. So Mercury is similar to Pluto. Callisto orbits either Jupiter or Neptune. This is a really more complicated form, but we can still break it into two separate thoughts, but the two separate thoughts are both about Callisto. So either Callisto orbits Jupiter, or OCJ, or Callisto orbits Neptune, OCN. There we have a more complicated form. Remember that we always have to put the and sign and the or sign between two statements. Things can be either true or false. We never put them between two names on their own or two predicates on their own. What really makes predicate logic interesting, though, is the use of quantifiers with variables. So quantifiers are the upside down A and the backward Z, and there are two quantifiers. So upside down A means for every value of the variable, or for all values of the variable. Backwards Z means there's at least one value of the variable. So there's some value of the variable that makes it true. So upside down AX means for every value of X. Backwards ZX means for some value of X. The simplest uses of these to translate things like everything or something or nothing. Everything is good means for every value of X, X is good. So upside down AX, GX. Something is infinite, so when you have something and we use the backwards Z, there is an XIX. Backwards ZX, IX means something is infinite. When you have no's or negations involved, you got to pay attention to where the negation goes. So nothing is free. There are two ways of doing it. You can say everything is not free for every value of X, not Fx, or you can say it's not true that there is an X, Fx. Those mean the same thing, but notice that the placement of the negation relative to the quantifier is different. That's not the same as saying not everything is free. So look at number 4, not everything is good. You put the not first before the upside down A. It's not true that for all X, GX. It's not true that everything is good. That's equivalent to saying something isn't good. There is an X, not GX. That's a kind of a weird way of translating that, but it's equivalent. Now you've got something like everything is either good or bad. This breaks the rule that usually use the upside down A with the arrow, usually use the backwards Z with an and. But here you're talking about everything, absolutely everything. So for all X, either GX or BX, right? But most of the time we don't talk about everything, nothing, or something. We talk about all members of some group, or every member of some group, some member of some group. And that's where these 4 basic forms get involved. So these are called categorical judgments, all blank or blank. You would say for every value of X, something about X, arrow something else about X. If it's some blank or blank, that's what we use the backwards Z with the ampersand. So backwards ZX, there's something about X, and there's something else about X. If it's no blank or blank, there are 2 ways of doing it. You can either say for every value of X, something about X, arrow not something else about X, or you can put the not at the beginning and use the backwards Z, not backwards Z, something about X, ampersand, something else about X. Some blank or not blank would be there is an X, something about X, and not something else about X. Notice that when you use the upside down A, you pretty much always use the arrow. When you use the backwards Z, you almost always use an and on the inside. Unless it's like number 5 earlier, where it's everything is either good or bad, where it's about everything rather than every member of some group. It's about every member of some group, there'll always be an arrow as the main operator if you use the upside down A. So be sure you don't use the wrong one. So you don't want to translate all birds fly as for all X, BX, and FX. That means everything is a bird that flies. You want to write for all X, if BX, BX arrow FX. If you're a bird, then you fly. Don't use the wrong combination. You've got adjectives modifying nouns, you've got combined predicates. You'll have a further set of parentheses and you'll join those together with and. Something similar happens with that, who, whom, and who, that, who, which, and whom clauses. We'll see the example of that in a second. Some democratic countries are socialist. There is an X. In further set of parentheses, you write DX and CX. X is democratic and X is a country, and X is socialist. Some socialist countries some countries are not socialist democracies. So here we have an adjective modifying noun in the grammatical predicate, so it'll be on the other side of the big and. So there is an X, X is a country, and it's not true that X is democratic and X is socialist. So you've got negations with these. You want to keep the negation outside of the parentheses. No planets that rotate are inhabitable. Here we've got a that clause. So that clause works a lot like an adjective modifying the noun. It's no rotating planets are inhabitable. So for all X, if X is a planet and X rotates, then X is not inhabitable. Right? So if you do it that way. You can also do it as it's not true that there is an X, PX and RX and IX, that you have and between all of them, and the not would be at the very beginning. Now surprisingly, sometimes when you translate statements that have and in the English, you want to translate them with an or. So if I don't have an adjective modifying a noun, but I actually have the word and, like all trucks and motorcycles are prohibited, the easiest way to translate that is actually with an or. You want to say for all X, if X is a truck or X is a motorcycle, then X is prohibited. You don't want to say for all X, TX and MX, arrow PX. That would mean everything that's both a truck and a motorcycle is prohibited. That's not what we mean. All right, so there's a bunch of practice translations here. I'm not going to go over that in my recording today. I want you to practice those on your own. All right, let's do some derivations review. I'm not going to go through all of these, but again, I'm just going to go through a few of them. So remember, for derivations, we've got 6 new rules in this unit. We've got universal out, what's true of everything is true of at least of any particular thing. Existential in, what's true of a particular thing is true of at least one thing. Existential out, what's true of at least one thing is true of something whose name you make up that is a new name. Universal derivation, if you have a show line to show a universal statement, if you can show it for a new name, then you could show the universal statement. And the negation rules, not everything is means something isn't, and not something is means everything isn't. So let's go through some derivations that use these rules. So this one, there is an x rxx for all x and for all y, rxy if and only if syx. Show that it's not true for all x and for all y, not sxy. Whenever you're trying to show negation, I recommend you do it by indirect derivation. So we're going to assume the opposite of what we're trying to show here. So the statement without the negation. Yeah, I can't type. Use show line to show a contradiction. So we've got an existential statement and 2 universal statements. We're going to do existential out before universal out. So I'm going to do existential out on 1, get RAA. And now I'm going to do my universal out. So the only letter it makes sense to do universal out in is to A. So first I'll change the for all x and 2 to an A. I'll leave the for all y alone. Just take the quantifiers one at a time. Change the x's to a's. Leave the y's alone. So we do that in line 2, I get this. I can do again on line 7, I get RAA double arrow SAA. Do universal out on line 4 as well. I get for all x, not SXA. Only change the y's, leave the x's alone. So sorry, for all x, SXA. So that's 4 universal out. Do it again on line 9, I get not SAA. So now I've got a 2-way arrow statement at line 8. I want to change that to a 1-way arrow. I can go in either direction, but since I have RAA, and it'd be nice if I got SAA, so that would give me a contradiction. I'm going to do it in that direction. So I have RAA at line 6, I get SAA. From 6 and 11, move ponens arrow out. Now I have a contradiction between 10 and 12. So I've shown splat, and I've shown that by indirect derivation. Very good. Let's move on to the next one. So this is a fairly complicated one. There is a friendly thing that respects all happy things. So there is an x, fx, and for all y, if hy, then rxy. There's something that's good and happy, so there is an x, gx, and hx. Show there is a good thing, for which it's not true that no friendly things respect it. So there is an x, gx, and it's not true for all y, fy, arrow, not ryx. So sometimes you can show existentials by direct derivation, but I'm going to show this by indirect derivation. That's what the chart says. Assume the negation of the entire existential statement. And we'll show a contradiction. All right, so I like to deal with negations of quantifiers before anything else. So I have a negation of a quantifier there at line 4. So I get for all x, not, in parentheses, gx, and not for all y, fy, arrow, not ryx. So the negation, if it's not true that something is, then everything isn't. So that's the negation rule, not existential out applied to 4. Now 6 became a universal out. I'm going to do existential outs before a universal out. So I'm going to go back to 1 and 2, do my existential out. So I get FA and for all y, hy, for all y, hy, arrow ray. I'm changing the x's to a's in 1, but leaving the y's alone. That's one existential out. Now I'm going to do another existential out on 2. I'm going to use a new name. I'm already using A, so I'm going to use B, GB, and HB. Now 7 and 8 are both AND statements that I can break up. So I get FA in one line. I break up 7. I get for all y, HY arrow RAY when I break up 7. I break up 8, I get GB in one line, HB in another line. 8 ampersand out. So I have GB and HB. All right, so what line haven't I worked with yet? Well, I haven't worked with the universal, so I haven't worked with the universal at line 6 or the universal at line 10. So I can do universal out on 6, whatever letter I want. Do I want to make that X an A or a B? Well, I think I want to make it a B because I have GB, but I don't have GA anywhere. So I'm going to do the universal out on 6, making the X's into B's. Again, you want to leave the Y's alone. So 6 universal out. I also do universal out on 10. Again, I want to make that Y a B since I have HB. So 10 universal out gives me that. Now since I have HB, I get RAB right away. So that's 12 and 14 Otis ponens. What do I do with that big statement at 13? Well, the negation of an AND statement turns into a conditional with a negation on the right side. So I get GB. If GB is true, then I move a negation over here. There's already a negation there, so I end up with a double negation. For all y, h, f, y, arrow, not r, y, b. So that's 13, not ampersand out. I have GB at 11, so I can get not for all y, fy, arrow, not ryb. That comes from 11 and 16, arrow out. Now I can drop out that double negative. Y, arrow, not ryb. 17 double negation. Now I've got a universal statement at line 18. I can make that y whatever I want. It makes sense to change it to an A since I have FA. So I get FA arrow not RAB. That comes from 18 universal out. Now since I have FA at line 9, I get not RAB. 9 and 19 arrow out. And then I have a contradiction between 15 and 20. Splat in. So finally I've shown splat, and I've shown that by indirect derivation. I probably made a mistake in here. We'll find out. Oh, nope. Did it right that time. Very good. All right, so let's do one more. Then I'll leave the rest for practice. So this one is interesting because it involves what I call desperate measures. Fairly complicated one, but we'll start it off just the way you start off any. So for all x, if it's true that if fx then hx, then both gx and ix, show that if for all x hx, then for all y gy. We'll start this just as a conditional derivation since we're trying to show a conditional. So conditional derivation, you assume the if part of what you're trying to show. You have a new show line to show the then part of what you're trying to show. Now this is a universal statement, so we're going to do this by universal derivation. So remember the way universal derivation works, there's just a new show line to show a new instance. So to show for all y gy, we'll show GA, where GA is a new name, right? We can show this however we want. When in doubt, if you're trying to show a simple statement, though, do it by indirect derivation. So we're going to assume not GA. Show a contradiction. Okay. So what can we do here? We've got a universal at line 1. We've got a universal at line 3. We can do those to A. So if I do 1 to A, I get if FA, then HA. If that, then GA and IA. One universal out. You can also do universal out on 3. I get HA. But actually, at this point in the problem, we kind of get stuck. We want to do arrow out on 8, but we don't have what we need to do arrow out on 8. We neither need to have the if part or the negation of the then part. If part to most ponens, negation of then part to most tolens. We don't have either of those, and we're stuck in this problem until we can do arrow out on 8. So what I call desperate measures is, if there's an arrow out or a wedge out you want to do, but you don't have the other thing you need to do it, write in a show line to get it. So if I could show FA arrow HA, then I'd have what I need to do arrow out on 1. So I'm going to show this, and I can show it any way I want. I'll show it by conditional derivation since it's a conditional. Assume FA, show HA. I'll just do this by direct derivation since I already have HA. So I can use that rule R. Write HA again down here. So 9R gives me HA again. I've shown HA. Therefore, I've shown this. Now, I still haven't shown the splat at line 7. But now that I have what I need to use line 8, right? So since show is crossed off at 10, I can use 10. And I get GA and IA from 8 and 10 modus ponens. That gives me GA, and I break that up. Now I have my splat, right? Now I have a splat between 6 and 15. Now I've shown splat, therefore I've shown this by indirect derivation, I've shown this by universal derivation, and I've shown that by conditional derivation. All right, so I'll leave the rest to you to do as practice. And that's it for the unit. That's it for the semester. Thanks so much for everyone. Hope you have a good summer, and I'll see you in the next one.